Good day, everyone. We're reviewing Wetzel's Limnology textbook. This is edition number 4, and we're on chapter 10, which deals with water as a chemical environment. And more specifically, we are in subchapter 3, factors regulating concentration of non-gaseous solutes. So let's get started. Equation 10-10 works well for predicting the mean whole lake concentration of total dissolved and particulate phosphorus and total nitrogen over many years in small oligotrophic lakes in central Ontario. Even though total phosphorus and total nitrogen inputs to lakes vary seasonally and annually, as do concentration within a lake. So let's look at equation number 1010 here. And we are looking at Cx is equal to inputs divided by V over Q, where V is generalized loss coefficient that represents all potential net losses from the water column, and Q is a water discharge coefficient representing loss via the outflow. Equation 10-10 works reasonably well for predicting mean long-term ammonium NH4+ and nitrate NO3- concentration in central Ontario lakes, with a variation of about threefold in net losses of V. The end cycle consists of numerous microbially mediated transformation producing and consuming ammonium and nitrate that are not explicitly described in equation 10-10. Equation 10-10 has also been successfully used to predict long-term mean concentration of total dissolved organic carbon and the humic or colored fraction of DOC in central Ontario lakes. The major external source of DOC to this lake is peatlands, and the major losses are from photochemical oxidation and microbial decomposition, which transfers CO2 to the atmosphere and DOC to sediments, perhaps via adsorption to settling ferron or iron hydroxide precipitates. The humic fraction of DOC is especially sensitive to solar radiation in the UVB and UVA regions, which cause photobleaching, loss of metal binding sites, and eventually oxidation of the carbon fraction to CO2. Steady-state equation 10-10 is useful for predicting long-term, multi-year averages, that there is too much uncertainty when used to predict outcomes over shorter time periods. For shorter time periods, dynamic process-oriented models should be used. The solution of inorganic iron is affected by the oxidation state of iron. Oxidation is a number of electron loss if the number is positive, or gained if the number is negative by atoms. There are two common oxidation states for iron in aquatic systems, with relative abundance of distribution between these two states controlled by pH and dissolved oxygen. The oxidized form, ferric iron, Fe3+, is sparingly soluble in the presence of oxygen at circumneutral pH and tends to precipitate as an iron hydroxide in the absence of a ligand, such as DOC. So 4 Fe3+ aqueous in water plus 12 water is equal to or results in 4 iron hydroxides plus 12 protons, where subscripts denote the phase. AQ is equal to aqueous, G is gas, and S solids. So we are dealing with this component here that is in water, and then we associate it with water. That's iron here, this ferric iron. It's combining with water, and it's creating a solid, which is this iron hydroxide, and it's creating these protons that are remaining in the water phase. The concentration of uncomplex or free Fe3+, which is ferric iron, in natural waters is too small to be measured directly and is instead estimated from chemical equilibrium models. This is a chemical equilibrium model. High total dissolved ferric iron concentration in circumneutral oxygenated natural waters are only possible when bound to DOC with binding sites, for example, humic DOC. Complexation to DOC maintains iron in solution, thereby lowering the total iron settling state, NV. The reduced form ferrous iron, or Fe2+, so in this case, it lost one electron, right? So instead of having 3 charges, it has 2 now. Is rapidly, and instead of being ferric, it's ferrous. Is rapidly and spontaneously oxidized to ferric iron. Oxidation is defined as losing one or more electron. Reduction is the gaining of electron. So here we are losing an electron when we are going from 2+ to 3+, right? Because an electron is negative, so otherwise it would be from 3+ to 2+, then we are getting an electron. Reduction is the gaining of electron in the presence of oxygen above pH 6. Consequently, free ferrous iron concentration are much lower than free ferric iron in circumneutral oxygenated waters and are said to be vanishingly small. And so this is the equation with ferrous, oxygen, gaining a proton, some proton, 4 of them, resulting in ferrous instead of, in ferric, and plus 2 water. And then the ferric is remaining in water. However, ferrous concentrations can be high in waters that are anoxic or acidic. Low pH inhibits oxidation to ferric iron, hence ferrous, produced by the photochemical reduction of ferric iron in surface water. Can accumulate, okay. Like ferrous iron concentration can also accumulate over iron-rich sediment in anoxic waters where the source is the microbial reductive dissolution of ferric hydroxide, because rapid oxidation of ferrous iron does not occur in the absence of oxygen. Thus, iron solubility is a function of several factors, including oxidation state, pH, oxygen, and the chelating capacity of DOC. So the chelating means the ability of dissolved organic carbon to bind, or ligand, as we saw that before. Since ferrous, ferric, phosphate, ammonium, nitrate, and solutes, such as other trace metals and major ions, are metabolically essential nutrients, concentration of these nutrients in the water column can be affected by phytoplankton demand, which removes them from solution. Cellular uptake transfers them from a dissolved phase across the cell membrane, which is then operationally defined as particulate because it no longer passes through a small pore filter. In some inland lakes in Canada, along Lake Superior, relatively abundant populations of cyanobacteria, which have an especially high metabolic demand for iron, draw down free ferric iron to concentration ranging from 10 to the minus 15 to 10 to the minus 10 nanomoles per liter. Subsequent sedimentation of senescent phytoplankton, so senescent meaning by that dying or old, phytoplankton cells transfers particulate ferric iron to sediments where iron is diagenetically processed into ferric hydroxide. So diagenetically processed means like it's sedimented. Should superficial sediments become anoxic, so anoxic means in the absence of oxygen, microbial reduction of iron hydroxides will release ferrous iron into overlying water, a process called internal loading. Phytoplankton productivity, especially picocyanobacteria, can sometimes be limited by low dissolved iron concentration. Metalloprotein, metal protein complexes are important cell constituents. The metal enzyme cofactors iron, manganese, and zinc are used by approximately 30% of all enzymes, while copper, molybdenum, nickel, and cobalt are used in smaller amounts. Iron is in greatest demand, constituting more than 50% of the intracellular molar trace metal content in marine phytoplankton and the bacterium Desulfovibrio. Thus, trace metals are involved in thousands of cellular redox reactions, including those in photosynthesis, respiration, nitrate reduction, urea decomposition, neutralization of reactive oxygen species, and nitrogen fixation. Hence, we can expect aquatic dissolved trace metal concentrations to be low where biological demand is high and supply rates are low. These are most likely to be productive waters in agricultural watersheds with low trace metal geology, little urbanization, and negligible industrialization. Factors regulating concentration of dissolved gases in water. Several gases are important to aquatic systems because of their metabolic roles. For example, oxygen, carbon dioxide, nitrogen, their effect on pH, such as carbon dioxide, or their role in climate change. For example, the greenhouse gases of carbon dioxide, methane, and nitrous oxide. Similar to non-gaseous solutes, dissolved gases dissolved gas concentration in lakes are affected by a host of internal processes that produce and consume gases, which are discussed in these chapters. Dissolved gas concentration are also influenced by atmospheric partial pressure, pH, temperature, and turbulence. This section discusses atmospheric exchange as a starting point. Movements or flux of a gas across the air-water boundary occurs when the dissolved gas concentration is not at equilibrium with the atmosphere, with the magnitude and direction of the flux depending on the difference between the actual and equilibrium concentrations. At equilibrium, the concentration of a dissolved gas in water is a function of the partial pressure of the gas in the atmosphere. The equilibrium relationship is given by Kh is equal to Cx divided by P by X, where Kh is Henry's law constant for a substance X. Cx is the dissolved concentration of the substance at the air-water boundary, and Px is the partial pressure of X in the atmosphere. Kh is negatively affected by increasing temperature, with cold water dissolving more gas than warm water. If X is oversaturated relative to the equilibrium concentration, then X degasses from the water surface into the atmosphere until equilibrium is achieved. For example, when high rates of photosynthetically produced oxygen concentration exceed equilibrium values, oxygen will degas to the atmosphere. If surface water is undersaturated, that is, if the gas concentration is less than the equilibrium value set by the atmospheric concentration, then atmospheric gas will invade and dissolve in the lake. Highly productive lakes draw down carbon dioxide below saturation levels during the growing season, allowing temporary atmospheric invasions. In contrast, oligotrophic lakes in central Ontario are typically supersaturated with carbon dioxide because of high inputs from streams and photomineralization of dissolved organic carbon. Hence, many streams and lakes in that region are CO2 sources for the atmosphere. Under non-equilibrium condition, it may be useful to estimate the magnitude of the flux or diffusive transfer of a gas across the air-water boundary, which is driven by the difference between the actual dissolved concentration at the air-water boundary and the equilibrium concentration. The flux can be given by F is equal to K, parentheses, X surface minus X equilibrium, where F is the flux, which is the mass of X transferred across the boundary per unit area per unit time. K is an apparent constant, the piston velocity, and X surface and X equilibrium are the measured and equilibrium concentration of the gas at the water surface, respectively. The constant K varies with gas, temperature, and turbulence at the surface of the water body. Gases transferred to the atmosphere can be transported long distances, which is an especially important consideration for volatile pollutants in surface waters and soils, such as mercury and hexachlorocyclohexane, which is a greenhouse gas. In summary for this chapter, water is a solvent capable of dissolving an extraordinarily large number of substances, that is solutes, providing a medium from which aquatic organisms can acquire substances. The 5 major classes of reaction that occur in freshwater are acid-base reaction, redox, photochemical reactions, complexation reactions, and adsorption-desorption reactions. The concentration of a solute in the water column of a surface water at any point in time is the net result of dynamic processes defined as the difference between inputs from all sources and all outputs, including transport processes and chemical reactions. Several gases are important in aquatic ecosystems because of their metabolic roles. For example, oxygen, carbon dioxide, and nitrogen, their effect on pH, such as CO2, or their role in climate change, such as these greenhouse gases. And that will conclude today's Chapter 10 presentation, and I'll see you tomorrow when we will be starting Chapter 11. And Chapter 11 will be entitled Oxygen. So we all need it. Talk to you soon. Bye.